So in this segment, we'll take a look at a particularly important statistical procedure, and that is the process of estimating probability density functions. So what does this involve? We acquire measurements from a large enough sample of representative situations. So let me underline large enough and representative. And we use these measurements and potentially other prior knowledge, let me underline prior, about the problem to construct probability density function using either parametric or non-parametric methods. So the rest of this short segment will focus on explaining what those words mean. But this is the process. We acquire a bunch of measurements from what's hopefully a representative sample, and we use some techniques, parametric or non-parametric methods, together with knowledge from other parts, other prior experience, to construct a probability density function. So let's just look at what this looks like. So we have first this condition of the sample versus the population. So we're interested in what happens in a population. For example, cancer patients over 50 years old. What we end up doing is studying a sample, some such patients. We recruit some of them that we can get our hands on, hopefully representative of the sample. And hopefully our results generalize to the population as a whole. And again, please always remember the goal of all of estimation here is to say something about the population. And so for that to be true, our sample has to be representative of the population. It has to be large enough so we can get conversions. Remember the discussion of the law of large numbers. And it has to be representative. It has to have the right type of people in terms of diversity of sexes, of ages, of conditions, of racial backgrounds, all of those things to sort of allow the results to generalize to the population as a whole. So this is where we talk about large enough and representative. A large sample helps with conversions, so our measurements are less sensitive to any oddball example. Our sample needs to look like a general population. And so here's a bad example. Drug studies used to be, and this used to be true actually, were tested on college students, and this failed to account for age, right? We're very young, healthy people, so the drug tends to work better. The same considerations apply to other things, sex, IQ, height, weight, and all kinds of variables. So these variables may not be applicable depending on what one is trying to measure, but this is something to be careful about. You don't want to weigh your sample so it does not represent the population appropriately. And the other thing I want you to note, and we'll come back to this multiple times, the commonly used hypothesis testing techniques when we do clinical trials, and we'll talk about them in a couple of segments here, effectively estimate the probability density function first. So if your sample in your clinical trial does not look like your population because it doesn't represent the population in many of these ways, you're going to estimate a bad distribution, and what you're going to end up with is a bad example. Your trial will be erroneous. The next word is this word prior, and this is a sort of enormous debates in the world of statistics. If you're a statistician, just skip this slide. Nothing here would be helpful to you. And the big question here is, can we use external information as part of the estimation? For example, can we assume that our data is smoothly varying over time? Can you use prior measurements for something similar? Those are fundamental questions in statistics. And this is a hallmark of Bayesian estimation. So let me give you an example. Let's go back to our opinion polling. And let's say we get a measurement for a particular state of what candidate A is going to do versus candidate B. Are we allowed to use measurements from the previous election to sort of say to smooth that out? Because we only measure 1,000 people, and let's say the state usually tilts towards party A. Maybe the poll shows party B way too high, and we think, well, you know, given historical knowledge, we're going to rescale this value because we don't really trust this. There may be an outlier. This is a type of thing that we call prior, and it's very valuable in statistics, and in many cases, when we have bad data, it can be extremely important to use this type of information. But again, there's a huge controversy in statistics whether prior information can or cannot be used. The next question is this question of parametric. Parametric assumes that the probability density function has a known shape with a known parameter. So let me give an example. Let's say you have this quadratic function. This is not a distribution, just a function, ax squared plus px plus c. We think the data follows this function, so we assume this form, and we just estimate A, B, and C here. So this is a parametric estimation. This is often simpler, and one needs only a smaller data set to get an accurate estimate. The critical question when you're doing parametric estimation is the model appropriate? So if we have used the wrong parametric function, the wrong distribution, we get erroneous results. And the classic method here in statistics, the one that everybody learns in their first statistics class, is what's called the method of moments. You assume a model distribution, for example, a Gaussian, you compute the mean and the standard deviation from the sample, and you plug these things into the model, or you use this to compute the parameters of the model, and there is your estimation, okay? Now, that is fine, but sometimes it doesn't work. For example, we can use non-parametric methods when we do not have a good parametric model. And often this involves the use of histograms and potentially additional smoothing. The advantage of non-parametric methods, where we make no assumptions as to the model, is that we make very weak assumptions about the form of the distribution. The disadvantage is that all of a sudden we need a ton more data. So let's take this example here. Let's say we have data that's distributed in this double hump way. If we assume the wrong parametric distribution, let's say we had a Gaussian with this kind of single peak, this would make no sense. It would give us erroneous measurements. The average of this distribution, which is probably somewhere around here, is actually meaningless because we have two peaks and the mean is not particularly presented. On the other hand, to estimate this entire shape, we would need a lot more measurements because instead of just estimating the width of this distribution, we're now estimating the value at every one point. And this is the problem now with non-parametric methods. So you pick your poison. If you have a good enough model and you have a sense of what the data is likely to be like, you can save a lot of time and get more accurate estimates by having a good parametric model. If you don't know what the distribution in the data is, then you have to resort to non-parametric techniques, and there you get into sampling issues and smoothness and all kinds of other problems. But they may still be your best guess as to how to model your data. So this concludes this discussion of estimation of probability density functions. In the next segment, we'll take a look at another important problem in statistics, and this is the problem of signal detection. Thank you.